We continue our coverage of polynomial and rational functions with a few installments on the basics of analyzing rational functions. This is a common Achilles heel in my experience because a lot of people will come into our course. It may have been a few years since they took the prior course, and in many cases the prior course, at least in my experience, it's not uncommon to find that rational functions are covered pretty superficially in those courses, especially if it's like a survey course like Math 70, which is our intermediate algebra, right? That class has a lot of topics in it, and so nothing gets covered to any great depth because of the wealth of material there, right? And so people come into our course and they frequently struggle with rational functions, but rational functions really isn't that difficult. If you understand some of the basics and you know what we're going to be asking, it should be pretty easy to deal with a little bit of effort. In our course, a rational function is just a ratio of polynomials. We do assume that they have real coefficients, and you can see a number of rational functions here on the screen in front of you. Now, we do assume some stuff when people come in and are studying rational functions. For example, we assume that people remember how to factor reasonably well, and that they have reasonable speed and accuracy when it comes to factoring. So we might expect, for example, and not be limited to, some knowledge such as the following. Look at g of x on the screen in front of you right here. You notice how the numerator of g of x is x squared plus 1. That's a sum of squares, and it's not factorable over reals. It is factorable over complex, but when we work with rational functions, we typically don't care to factor things that are factorable over the complex numbers. We just want the stuff that factors over the reals. So we would assume that people know, that when they come into our course, that x squared plus 1 can't be factored over reals. Likewise, when you look at I of x, you notice how the numerator of I of x is x cubed plus 1. We would assume that people know that that's a sum of cubes and that it can be factored using a famous pattern from algebra class, right? Likewise, when you look at g of x and I of x, the denominators of both of those, which would be x squared minus 9 and x squared minus 4 respectively, the denominators of both are difference of squares pattern, as is the numerator of h of x, and part of the denominator of h of x is as well. So we expect that people can recognize difference of squares and they know how to factor that, right? And so if you're rusty on the factoring, we don't really cover that in this particular series of installments. You'd have to review that material kind of on your own time. YouTube has a wealth of resources and some really excellent videos that'll help you to do quick factoring review if you need that, but we just don't have the time to offer it in this series here. So here's a generic rational function. It's pretty common in many books to see them using r of x to represent rational functions for obvious reasons. P of x is usually, or is often used rather, for the numerator polynomial, and q of x for the denominator polynomial. And the only reason we're showing that here is just to make some of the notation that we're going to be using plain. So for example, it's important that you be able to recognize the leading coefficient of both the numerator and the denominator polynomials, and so that's one of the reasons that we put that generic up there, because we use that notation a sub n and b sub m to represent the numerator and denominator leading coefficients respectively, and likewise the constant terms and the degrees and everything like that, right? Now, even though these rational functions are typically presented in this form where both the numerators and denominators are not always going to be factored, when you do analysis of these, that's usually the first step, is that you factor the numerator and denominator both completely, and for that reason, that's why we're emphasizing that you have to have some factoring game when it comes to factoring polynomials. So what are we expecting from you? Well, we're expecting that you can handle the basics. So the basics would include, but not be limited to, that you can find the zeros of both the numerator and the denominator of a rational function. And you would understand how those zeros are going to show up on the graph. For example, numerator zeros typically show up as x-intercepts, and denominator zeros typically show up as vertical asymptotes, but not always. There's some exceptions. And so we would also expect that you can find any asymptotes, at least the vertical and horizontal ones. Sometimes textbooks will ask you about the slant asymptote or the oblique asymptote. And that was more important back in the day before graphing calculators were prevalent and cheap. And so, we may field that in a few examples, but generally that's not really something that we're interested in because the graphing calculator can take care of that for you. We're interested in the end behavior, and that refers to how the polynomial, how the rational function behaves when the input variable x gets large and negative or large and positive, and likewise how it behaves around the asymptotes. And you'll see down the road, many people take our course not for their own health, but because they're looking to take something else down the road. And so this knowledge of rational functions, it's in here for a reason. It's not because we enjoy covering them or that you enjoy us covering them. It's because you're going to need that down the road in some course that you're going to take. So let's cut to the chase. We have some nice examples for you, and as with the polynomials, we usually start with the graphic examples because those are the best. They help people connect with the material most rapidly. Let's take a look at what we've got here. So our instructions are: take a look at the graph and come up with the intercepts. That would be both x and y, the vertical and horizontal asymptotes, and give us the domain and range in interval notation. So first example is this one here. And if you look at it, typical rational function, you'll notice that there's some dashed blue lines on the graph. Those are representing vertical asymptotes. Sometimes they mark those, sometimes they don't. If you look at this very same function on the graphing calculator, the vertical asymptotes will not be marked, nor will the horizontal asymptotes. So you kind of have to practice a little bit to develop an eye for these kinds of things. But let's answer what they're asking here. The first thing they want to know is the intercepts. So the intercepts are where the graph crosses one of the axes, and you can see that in this particular case, the function crosses the axes at the origin. So in other words, it crosses both x and y at the same location. Coordinates of that are 0, 0. So if we're making a list of answers here, the intercepts now, sometimes the learning management system is content to accept a single coordinate, and sometimes they want an ordered pair. So you kind of have to look at what your learning management system is requiring. But you could answer this a couple of ways. You could say x is 0, for example, which is perfectly reasonable. Or you could say 0, 0 if you have to give both coordinates of that point. In a similar fashion, the y-intercept is y is 0. Or again, if you had to give ordered pairs, it's 0, 0. So they both cross there. Next thing we're asked is asymptotes, vertical and horizontal. So we already mentioned the vertical asymptotes. And when you look at this graph here, you notice that they're not using the same scale on both axes. They are using one hash mark to represent one unit on the y-axis, but one hash mark on the x-axis represents half of a unit. So you got to be really careful when you're reading it. It's easy to mislabel things, especially when the labeling is minimal as it is here. So my vertical asymptotes, which I abbreviate for obvious reasons, VA, those are located at x is -1 and x is +2. They're both vertical lines, and they are they're boundaries over which the function does not pass. Now the horizontal asymptote, if you have an experienced eye, it's easy to read. In this case, the horizontal asymptote is the x-axis, otherwise known as y equals 0. The horizontal line, y equals 0. How do we know it's got a horizontal asymptote there? I mean, well, experience, like I said. We'll get into some additional examples down the road that'll hopefully help to build experience. But for the moment, suffice it to say that it does indeed have a horizontal asymptote. Maybe it would be nice if they had showed us a little bit more of the end behavior, but there's enough there that you can read that. And so even though it's not marked on the graph, it's clearly a horizontal asymptote. Just as an aside, one of our kind of holy grail problems that we do down the road, and we would be delighted if everybody was capable of doing this, is to take the graph of a rational function like this and to come up with a possible formula. It's really not as hard as you might think. And it's a great way of sort of synthesizing all the different kinds of things that we want into a single problem. And so, that's one of the reasons I can tell you that it's got a horizontal asymptote on the basis of kind of knowing what the formula would have to have in it. Anyway, the last thing they ask is the domain and the range. So as far as the domain and range, let's chat about that. So the domain is where the function is supported or where the function lives on the x-axis. And so if you ask me to shade it in on the graph, I would say, well, you have to exclude the asymptotes because those are values that are not in the domain because the function is not defined there, right? But the rest of the domain would look like this. You have this piece here, and then you have this piece here that goes in between, and then you have this piece out here. And so you have to represent that using interval notation. That's the usual way that they want that. And so the domain in this case would be as follows. It's the interval from -infinity to -1 with round parentheses on the ends there. Union -1 to +2. Union +2 to positive infinity. And so if you're rusty on the interval notation, another common Achilles heel, I hate to say, but we don't really have time to review it in this series. That would be another thing that you can find on YouTube or somewhere else and you can review there. It is very common that people are kind of iffy on interval notation, particularly at the beginning. Anyway, as far as the range is concerned, let's color code it. The range is where the function lives on the y-axis. So even though it's true that we have a horizontal asymptote at y equals 0, the function actually achieves that point because it passes through the origin, right? And so you can see that the function is going to eventually spit out every value on the y-axis. And so for that reason, the range is the interval from -infinity to infinity, right? Let's see what we have for the next example. Here's what's next. Same instructions. So we want to know what are the intercepts, if any, and we want to know about the asymptotes, and we want to know about the domain and the range. So as far as intercepts are concerned, you can see that the graph is again using a scale which is labeled in what could be a confusing way. It's actually not. So they're using the same unit on both axes. Each hash mark represents 2 units. So you can see you have x-intercepts right here. Well, let me circle them in a way that's visible here. Something like that. I don't want to leave those there because I'm going to erase them. But anyway, for x-intercepts, you could say that x is positive or -2. Again, your learning management system may not be wild about that, so you may have to give coordinates. That would be 2. There's -2 and 0 and 2 and 0. And as far as the y-intercept is concerned, you can see that it's at -6. If you had to list it as an ordered pair, it's 0, -6, right? Okay. Let me get those circles out of the way there. It's kind of raining on my domain and range parade. Number 2 would be asymptotes. And you can see you have a horizontal asymptote here. They helpfully put a dotted blue line right there at y equals 2. But there's no vertical asymptotes in evidence. And so it's true that some rational functions don't have them. I mean, it kind of depends on what you got, right? We'll see many, many examples, and we'll have plenty of time to talk about that. But anyway, for vertical asymptotes, there are none. And for the horizontal asymptote, that is that y is 2. And then the next thing we're being asked is domain and range. So as far as the domain is concerned, it's going to be all real numbers. The function is clearly supported on the entire y or the entire x-axis, right? So it lives everywhere on the x-axis, and for that reason the domain is negative infinity to infinity. As far as the range is concerned, it's not everywhere. And actually, the function does not achieve y equals 2. It approaches that horizontal asymptote as closely as you may want, but there's no value from this function that you can't put any x value into the function that's going to cause it to spit out y equals 2. So your range is going to have an open circle right there, and it's going to have a closed circle at -6, and it's going to be all of this, right? And so if you represent that in interval notation, you start at the -6, and so you're going to have a square bracket on -6 because it's included, but you're going to have a round parenthesis on the +2 because it's not. And so that's a great example of where, being a little rusty on the interval notation kind of drives people crazy, because they might type something into their learning management system. And over the years, I've gotten a lot of emails from people where they're angry because they were marked incorrect, and they send me a screenshot or something, and it turns out that they were in the wrong, that the learning management system was correct. It's just that they were rusty on the interval notation. So if you have to brush up, feel free. Stay tuned for the next video.